Great. Let's start with fatigue and variable load, meaning kind of, well, it's the name of the slide is stress concentration and variable load. In deep focus is based on fatigue. So why metals or any other material would fail kind of as something called fatigue. In the course, we have talked from the beginning that our mission when designing structures, if we focus only on steel or kind of construction, is to make sure that the design is not going to fail because it breaks, meaning that it just, the loads surpass the yield strength or ultimate strength of the material, and then it breaks or it deforms very at a high level that, it just the use becomes uh, kind of not possible. So we have determined those two type of failures. Now we're going to talk about the third type of failure, which is basically close to the same as the first two as the static failures that we have seen so far, but with a slight differentiator, kind of another piece of information that it's going to give us. And just to remember, kind of fatigue is not applied to everything. We can find out, we can see, we can investigate is if the design we are, say, developing at the moment has to be designed according to certain fatigue criteria, but not everything is designed according to fatigue. Now, in this slide, you have a picture there, and it's a shaft, right, this one here, and this is a typical fatigue failure. And you're going to see two big areas. You're going to just draw this line. So this is this green line here, the one that is on the bottom. This one here is one part of the fatigue failure, and this is the other part, kind of represented by the whole or the rest of the part here, this one here. So what happens is that when this shaft is working, fatigue failure starts. We don't know at the moment. It appears in the material later why fatigue failure starts, but starts failing because of fatigue. And then this whole piece of the shaft has a different, let's say, presentation or surface uh, finished finish, sorry, than the other one. And the fatigue starts and starts, let's say, starts, failing. What it means failing is kind of there is a small crack here. They're going to see later that appears also there. And this small crack keeps growing and growing and growing until it reaches kind of this level here. And when it reaches that level, the rest of the material that is left, which is, imagine that if this was the original diameter of this shaft here, and you design that shaft for its purpose, you say, well, the diameter, I have to use for this design has to be D. However, when it failed, the final diameter that was able to support the whole bunch of loads on that shaft was this one here. Let's put it this D2, and let's call this D1. This is your design diameter, and this one here in green is the failure diameter, meaning that the part still worked even though it didn't have the corresponding area section needed to, let's say, that you kind of prescribe at the beginning, meaning that it could work with less diameter, meaning that you could use a smaller diameter for your purposes, but well, it failed. But the fatigue failure means that it's going to the part in this case is going to fail because the remaining structure, after this part here was affected by a big crack in this section, well, the remembered part still could do the job until, a diameter 2 where, it was not able to hold the forces anymore and it broke. So there's a difference between the design diameter and the diameter at which it breaks. And this big difference is going to be depend on which safety factor you used for your design, which type of considerations, which type of failure design theory, and so on, and and other unknowns that we're not taking into account. Remember when we talked about materials that the yield strength of material is determined statistically, meaning that there is a lot of information left out, and we are, in a nutshell, in a simplistic way, using some set of averaging. And averages in statistics tell you half of the truth. So it could be more, it could be less. It depends on more or less what type of procedure we use, what type of standards were used. For example, when manufacturing that type of material, which things that we cannot control, but the manufacturer has to control it at a certain point, but there are ranges. So there's a bunch of details when calculating, and then that's why those values we are using as yield strength for the material can be even overestimated or underestimated. That's kind of the difference going to be related to that. And one of the specific, say, characteristics of fatigue and fatigue failure has to do with this thing here. This is called variable load. Static case, we don't consider fatigue as a predominant failure mechanism. In equipment, machine elements that are moving or subjected to a variable loading, then we can say that yes, fatigue might be a possible failure mechanism of that part. Hence, I need to make sure that if it is that so, I need to certify or validate within my design that the part is not going to fail uh, due to fatigue, the fatigue mechanism in that case. You are always going to be able to recognize if something failed, or in most of the cases, you are going to be able to recognize if something failed due to fatigue. And one of the cases is because of this separation of ways in or surfaces in the affected area of the part. So you have a very well sort of polished area here, and polished because as this was cracked, and meaning that the other part of the shaft separated at this point. So at this point, the relative movement between the two pieces kind of uh, polishes this part here. And then when the part is not able to withstand the load, it just tears up completely. But this part here in the bottom is more or less going to be sort of polished. And in addition to the variable load, then fatigue might also be influenced by other factors that we haven't considered so far, which are, for example, even the size of the part affects the fatigue, let's say resistance of the design, how the load varies. Yeah, variating load is not just a characteristics, but the variation has itself an important way of defining that variation. Temperature, where we are going to be operating our design, and kind of the atmosphere that I believe I mentioned that some classes back, that you can have a design or a machine element operating in a kind of an acid atmosphere or kind of extreme atmosphere, that it makes complicates things, and you have to take that into account. So it is important to understand that variable load, the type of variable load, and then the conditions surrounding the parts are going to affect how well it's going to withstand fatigue failure. This is another shaft that failed, and besides kind of being able in most of the cases of knowing if a part failed due to fatigue or not, you could be always you could always assume where the fatigue failure started. For example, this is a shaft, and what you have here at the top is what is called a keyway. And the function of a keyway, we should know that, is to hold a key here. And this key, its only purpose is to kind of be used as a reinforcement to avoid any relative movement between this piece of the shaft here and whatever you mount on top of that. For example, on this surface, you might have mounted a coupling, and that coupling might be kind of mounted on top of the shaft, and then you are using this key as a extra guarantee that the coupling, if it's moving in this direction, the shaft is not going to slide inside of that coupling. I hope that picture kind of gets a little bit, or is a little bit clear. But the purpose of a key is to guarantee that there's not going to be any relative movement between those two parts that are going to be mounted one on top of the other. Now, in this specific case, for this figure, it is said that the failure sort of started here. Let me put it with another color. And the reason for that is that if you notice that the surface of the shaft, kind of in the exterior part, is very, very well, let's say, consistent and smooth, but in this keyway, you're going to find that there are some kind of sharp corners here, these ones here. So these sharp corners, what they're going to do is that it's going to increase the kind of the stresses in these small points here are going to be higher than in the rest that it should be in the rest of the material. And what's going to happen that as it is higher, it is possible that this increased stress in that area surpasses the yield strength of the material, and then it kind of deforms, or it surpasses kind of in that small spot the ultimate strength of the material, and then it creates a micro crack, a small crack there. And then that crack is the point of initiation for what it comes rest, which is the fatigue or the failure or complete rupture of the whole shaft. Now, in this specific sample, of course, I don't know what were the loading cases. I don't know the operative conditions, such as, as a shaft, it was rotating at which kind of a speed was rotating. I don't know that, but you can also differentiate these two areas. You have the polished area here, kind of that follows this part here, and you have the kind of sudden rupture area, which is this one here. Yeah. So imagine what it took to break this. So most most that more than half of the shaft was broken, let's put it in that way, was cracked, and still it could do the job. Again, I don't know which were the loads applied on the shaft, or kind of the application, or the operative conditions like an operative speed or anything like that. But it took more than half of the shaft to break. Kind of look at this. Just this part was doing the job. And this is amazing. And kind of I have presented two figures of shafts because, as they're rotating and rotating maybe at higher speeds, then it is very common to find fatigue failures on shafts. But fatigue failure it can be kind of, it affects everything that's subjected to a variable load, and a variable load that can be considered as a shaft, as a fatigue failure mechanism, or for a fatigue failure mechanism in that sense. Now, what I mentioned about answering those two questions proposed at the beginning of the class, which were first asking myself during my design process, is this part going to fail? And the second one is this part going to deform beyond usable limits? Then what fatigue failure in this case is going to bring to the table is the following thing. Let me see if I can find it here. Is, okay, it is not only that it's going to break, but when it is going to break. And look at this part here. So when you use fatigue design, you you are saying that, okay, yeah, my part is going to fail, and it's going to fail at this kind of time frame. Let's put it in that way. Or no, it's going to last, for example, that sentence I added there, that, hey, you know what? This is not kind of, I decided this machine element, and it's not going to break, it's not going to deform, but it will break in the next 30 years, or at the end of 30 years, if you use a part, under the design loading conditions, taking into account for the design redundancy there. But if you operate that machine element at, for example, 8,000 cycles per year, then it will last 30 years. So not only you are saying that your part is not going to break right now, but it will break, at the end of 30 years. And actually, many of the equipment you see in the industry, they estimate that equipment is going to fail at a certain point of life, because I believe I mentioned also during one of our classes is that when you design something that is going to be subjected to variable load, that's going to break. At some point in the life of that equipment, it will break. And it's your job as a designer to give an estimation of on when it's going to break. So it's not only that you design the part and then it is kind of an appealing design because the aesthetics of it is nice, but also you need to also give that information that if this part is used according to this condition, it's going to last 20 years or 30 years. And that's part of the designer. Uh, for example, in the company I work for right now, they design equipment, industrial filtration equipment, which are machines in the size of kind of maybe 4 meters, 5 meters high, 6 meters kind of long, and then kind of 3 meters wide. So they are big machines. And then I remember one of the discussions with the design engineer, And he mentioned, exactly like that. We have designed this part so it lasts, 25 years, 30 years, according to this loading regime. So they have to take in consideration, and we have to take it into consideration for our designs. And fatigue is going to help us do that. However, let's remember something important, that fatigue design is based on an experiment. So there is not a strong analytical, it's kind of alone analytical tool derived from the physics, but it is highly dependent on statistics and experiments. And mentioning or reinforcing that whatever you do in statistical measure on top of statistical measures is something that you need to be careful with, that because it's not a precise forecast about what's going to happen. So yes, you might say that this is going to last about 30 years under this loading regime, but that's not sure. That's not sure because first, you are not completely sure about the all assumptions you have made, and you cannot be completely sure because there are many different and complex relations that you don't know what's happening there, but you do your best estimation about them. Secondly, once you design that part, the part is going to be manufactured, and the manufacturing process, people can induce without knowledge or due to the manufacturing process used, can induce small possible failure or kind of minimum microscopic kind of points of failure that you are not aware about or you have not considered. And thirdly, kind of after that part is manufactured, that part is going to go to an user, and you don't know how that person or team is going to use that part, meaning they can overload that. Yeah, you say, well, no, I'm going to work 8,000 cycles per year, but it could be 10,000. It could be 12,000 because they kind of are using it for other purposes. And you might say that, well, this shaft, the torque of this shaft, I'm just going to say a number, is going to be about 30 kilo newtons per meter. Yeah, but when people start using this equipment, it turns out that they ramp it up to 50 kilonewtons per meter. So you don't have control about that. So you have given your indications, but you don't have control over so many things, over so many hidden features, that saying that this is going to last 30 years based on certain loading conditions and utilization is always going to be an approximate. You have to give it, but it's always going to be an approximate, and that's something that you cannot put your money on that say, yeah, it is going to last. No. What questions do you have so far? Then where the fatigue starts, kind of, is there something that we could do? Well, yes, as I mentioned, fatigue usually starts in a small crack, a small kind of micro thing that usually in the surface is where it starts. And we say usually in the surface because the surface is exposed and the surface is prone to these beginnings. And usually in the surface is where the maximum stresses are going to be found when you kind of calculate something. Let's remember the example of the beam or this rounded bar in the evaluated exercises concerning failure theories. So you're going to find out that in most cases, the maximum stresses are going to be found either in the surface or in these discontinuity points where the section changes or there is a keyway or something like that, but it's going to be highly associated with the surface. And again, it's going to start there because the material is going to fail at certain micro spot there, and that small failure is going to initiate a crack, and that crack is going to start growing and growing, growing until the part fails. Kind of in a nutshell, that's kind of what's happening with fatigue failure. And if you look at the material I posted about the exam applied last year, I believe one of them is kind of explaining how the fatigue failure originated. And everything was here. And it's not something super complex to define. Kind of, I believe this was one of the questions on the exams that said, can you explain how the fatigue failure starts? And then, well, it starts because at some part of the material, most probably the surface, a micro crack initiates the whole process. That cracks start increasing because of the variable load, and then until it gets to the point that the remaining section of the part is so small that it cannot withstand the whole forces, and it breaks. And that was it. That was the whole answer to that question. It's very well summarized here. And yes, it's most probably that the fatigue failure starts at the surface because, as I mentioned, is where it's more prone to have it. Either because when you manufacture the part, uh, in the process, something was it's a micro, not it's not a failure, but kind of an irregularity kind of started on the surface, and then everything went downhill from that. Of course, cracks can exist also in the interior of the material, and that would depend on the quality of the material you are using. And also that's tightly related to the manufacturing process of the material, because if you have certain, imagine in this point, you have certain pores or kind of empty voids here that there shouldn't be there, but appear because of the poor manufacturing process, not even poor manufacturing process, but the the poor quality control during the manufacturing process, then you can have something here that is going to increase the stresses in that area, and then everything can originate from that. But we can stick to this definition here, or on where fatigue starts and how is the whole process, and it's pretty simple. If you put it like that, it's pretty simple. And as an engineer, let's try to keep things simple in the sense that somebody asks you about, hey, how fatigue starts. Well, because there's an imperfection. That imperfection generates a micro crack, and then from that micro crack, everything starts, kind of, it starts growing until the remaining section holding or trying to withstand the forces is so small that it breaks suddenly. And that's why you're going to see in fatigue failure these two sections. So if you put it in that way, it's done. It's just done. And basically, that's the way to define fatigue failure in a short sentence. Yeah. Then, so in our future parts, or in the past, when we're dealing with static design, we consider yield strength of the material to determine if the part is going to deform or not, and we considered the ultimate strength of the material to determine if the part was going to break or not. Is there something similar for fatigue? Well, the answer is yes. And the word to define that specific number that we need to take care not to exceed, because if not, we're going to be prone to have a fatigue failure in our design, is called, as you have it there, kind of, it's going to be represented in several ways, like Sn or S prime n is called fatigue endurance, or kind of a limit endurance, or fatigue limit, and this kind of stuff. Then one thing important here is that, yeah, we're going to have yield strength, we're going to have the ultimate strength, and we're going to have this fatigue strength, or limit, or endurance. You're going to find it like S here, or you're going to find that I have written it like this. So I'm going to use interchangeably those two terms. Actually, like this. And the prime symbol in that, let's say in one or the other, kind of, if you use what's the difference between this one here and this one here? Well, both refer to the same. The difference is that this is related to the material itself and is determined experimentally on your part. So this is a experimentally determined uh, value. Yeah. And the other one is that the one that you're going to calculate according to your loading case to compare to this one. Then questions would be, okay, but how do I calculate that? So if I try to make a comparison between what we did in static design with this variable load design, is, okay, I know that in the past I've used, depending whether the material is ductile or fragile or brittle, if it's, I'm going to use Tresca or von Mises failure theory. So is there something similar for stresses? Well, the answer is yes. But before we get to that point, let's watch something happening. I thought it would be interesting to watch a couple of videos that I found. So these videos are not in the material I posted in Moodle, but I just said, well, why not, if we're kind of streaming this virtually, and I can embed some videos and we can have it and discuss it. So why not to put some videos about fatigue failure? So I went on YouTube and found about 3 videos about fatigue failure, and something that is interesting mentioning, where we can see fatigue failure developing over time. Now, this is very kind of important from the engineering point of view. Yes, so if I'm doing a calculation of a part, and I'm going to say at the end of this design process that that part is going to last 15 years, and I want to, let's put it in this way, validate that, yeah, it's more or less 15 years, 15 year plus minus something. Would that mean that I have to manufacture a part and test it for 15 years? So it doesn't make sense. So if I want to have a real case scenario experiment on the fatigue failure of the part, so if I decide something for 30 years, it's not scalable, it's nothing logic to conduct a trial for 30 years to see if you were right or not. So there are mechanisms where that you can use to speed up the failure, and then you can scale up that reduced time failure and say, well, yes, it's more or less 30 years. No? And in a nutshell, you can do that by either increasing the loads on your parts or reducing certain sizes or scales in your design, but everything has to be done according to certain simil the word for that is similarity laws. Then you can scale back to the original part and see, well, yes, it's about 15 years, but no way you're going to perform an experiment during 15 or 30 years to see if in reality your design was correct or not. That's not done. That's not done. So, but I want to show you next is, for example, one type of a video of these tests rigs used for fatigue failure, accelerated fatigue failure, and accelerated because you either impose uh, a variable load, which is the magnitude is higher than the one you're going to physically experiment in during the life of the equipment, or you just increase the frequency of the application of that variable load. So those cycles to break, because let's remember that when we define that the part will kind of last 30 years based on an average of 8,000 cycles per year. But what about if me doing 8,000 cycles in a year, I do 8,000 cycles, for example, in 1 month. And then it means that those 30 years could be reduced to 30 months and then or way less than that. So you can conduct these kind of experiments to certify that to a certain level that indeed is going to last for 30 years. But let's take a look at that. This has a sound, so I will try to decrease the sound of this while I start, let's say, describing what's happening here. But this is found on YouTube, and I want you to focus in this area here. So this is a aluminum beam. I think so, yes. This is an aluminum beam, square beam. And imagine that this is a kind of a, there are forces being applied toward, let me try to write this. So there's a force kind of being applied in this direction, up and down, well, mainly up. And then there is some sort of restriction of movement here, meaning that this whole piece here cannot move here, but it's going to have two forces applied here, meaning that there is a reaction force applied in this point. And then this is going up and down, which simulates this variable loading, meaning is loading, unloading, loading, unloading, and then that's done for a series of time until the failure appears. I don't remember exactly for this video, I should have noted that, but I have the address somewhere. That what were the characteristics of this test rig and experiment and how long did it last, because that's important also to know what's happening here. But this is an aluminum beam. I'm unaware of the dimensions of it, so I cannot comment on that. But the phenomenon still, it is self-explained, and it's better to see it than not seeing anything. So let me put it to roll here. It should start. Let me go back and up. No, it's not starting. Let me see another one. Hmm. Just when I thought. No, it doesn't start. Sorry about that, guy. No, it doesn't start. Oh, my bad. Ah, I know maybe why. Now it should start. No, of course. Let me see preview. There you go. Yeah, you should see it moving now. So here's what I mentioned. It should be focused on because a crack starts. Okay, let me stop here. So I don't know if noticeable in your screen, but there is a small kind of crack. Well, there was small crack appearing here. So let's try to watch it again. Preview. And it says that it was 30 hertz on the minute, 30 seconds, 30 times per second. This thing is kind of moving up and down. Let me delete this again. Let me roll it completely. Yeah, 20,000 per each, 15 minutes. So I don't know if you start seeing kind of where I mentioned that the crack starts kind of increasing, but by the end of the video, you're able to see kind of what a huge failure, let's say, here, and then how it ends up breaking. Yeah, this is larger and larger. Look at that. So that crack keeps increasing and increasing. Yeah, this is amazing. I have seen this happening in real time in the industry, and it's just a clear recipe for disaster. You cannot do anything to hurt this. Once it starts, it's going to break. The only thing you can do is just you can try to repair it, you try to re-weld the crack, do certain measures on the kind of on a certain part of the failure, but you cannot do anything else. It just fails. You need to replace the whole part. Look at that. It's amazing. That's what it's called, fatigue. Yeah. Now this is just kind of a uh, a simple bending moment applied to this beam, meaning you just apply lateral forces to the beam and then release the force. Apply lateral forces and release the force. Now this other part is a little bit different because this is a rotating shaft, and this shaft is subjected to reverse bending. And when I say reverse bending, is that these two motors that you have here, or one motor and one, let's say, one driven and one driver, they are not exactly aligned, but they are a little bit misaligned, inducing some bending on this shaft here. And let's see what happens when you start. Okay. I believe this is a bit fast. So that misalignment is going to induce reverse bending on the rotating shaft until it just breaks solid. It's about to break now. It didn't break. I thought it was going to, but it breaks. Actually, the video breaks at me. Uh, I have seen also these type of failures in the industry, and most of those failures, believe it or not, would happen in certain points like this key wave stuff. But this is the type of setting that you use for a reverse bending type of variable load applied on this rotary shaft. But I would pass you also the this video because it shows how it just breaks. I don't know what I didn't have the full. And another type of failure that you can have, this doesn't show any failure part or something, but it's interesting that this is possible also to have or to see. Look at that. This is actually a bicycle, and they're trying to test it to guarantee that it's going to last about 40,000 kind of kilometers without any type of maintenance. So imagine that. So this is very interesting. I believe this type of fields in mechanical engineering kind of area is very interesting, the testing area, because you get to do this kind of fun stuff and cool stuff that is not something static, kind of designing on a paper, which is also interesting, but in this case you get to experiment at first hand if those designs proposed are going to be valid or going to be close to what they are assumed to be. But this is very interesting. Any questions? No. All right. Now we have seen that it fails, and then yeah, you cannot do a test for 30 years, but you can speed up those tests by applying certain mechanisms and strategies. Then we can enter to talk about what is fatigue endurance, how is determined, and everything. And let's see. When we talk about fatigue endurance or fatigue limit or fatigue strength, I'm going to use that interchangeably along the whole presentation. Is a value that comes from testing. For example, you take one specimen. When I mean one specimen is one design, one piece of material, something like this. One specimen is this. When it breaks, then you bring another specimen and test it. So this is one specimen. And then imagine that, with the test applied here, you were applying, well, if I remember correctly, they were applying about 20,000 pound per square inch. And, they were applying it at 30 hertz, meaning 30 times per second, they were applying this 20,000 KSI. And when it breaks, they take note and they say, for example, here, okay, at 1,000, at 20,000 KSI, it lasted, for example, let's take this point. At a, let's imagine that this is about, 20,000 KSI, 20 KSI, and then it lasted something like this, and then this many cycles. So you have how many cycles it lasted, you have, the force applied there, and then you mark a point here, and then you start doing that for different, not for different, for many specimens. Kind of you start seeing where they fare. You increase the, let's say, the stress of the force applied, and then for sure, if you increase the force, they are going to fail earlier. And then if you reduce the force, then they are going to, let's say, fail. They're going to take more time to fail. And then they're going to have this kind of curve. And this kind of curve, where you plot the results of your tests of, stress applied versus the number of cycles it took to break, usually takes this shape. And And what you have here is that when you transform that into something usable, like here, in this point here, you're going to find that the curves can be more or less, almost most of the materials can be approximated to this shape. Look at this. So they have a downward kind of or decreasing line when you kind of fit all these, let's say, points towards kind of using some kind of a fitting process, and then some sort of straight line here. When you can find a material that follows this shape here, then this part that you find in here is considered to be the endurance limit or the strength, fatigue strength limit, and so on. Let's call it endurance, fatigue endurance. So this is the fatigue endurance. On the other case, where you have materials that they don't follow the same shape, then, like in this one over here, and let me change the marker to draw that one. Then what you say is that for the yellow case of the first one is that there is an endurance limit, and then for the other case, the green one, there is not an endurance limit. Now, the endurance limit is a very important factor because, among other things, it's going to allow us to design on our parts based on fatigue. And also, later, we're going to see that it's going to tell us which is the amount of stress applied to the part that we can consider that is not going to induce any fatigue on the part, meaning that I don't have to design for fatigue. So that number is very important. But as a number also derived from experiments, derived from statistics and approximations and fitting processes, is going to be subjected to many, many, let's say, inaccuracies. And assumptions can be very destructive in our engineering field. So we need to take care of trying to account for many, let's say, unknowns happening here. And we do that by applying certain, let's say, factors to that we will see later. The materials we're going to use here follow what I mentioned, kind of this type of shape. Where this one here is the endurance limit. Yeah. Some others are going to have this kind of shape, but it's more or less similar. And one thing we need to have present when dealing with fatigue is that when a part is subjected to variable loading, we can classify that part into a high cycle operative part or low cycle operative part, meaning that if a part, when I do the design or calculate everything, say Let me give you a very brief example. In here, for example, if a part say that lasts more than 10 a la 3 cycles, we are considering that that's a kind of high cycle or a part that's going to, let's say, last a large number of cycles. And at some point, we are going to take a look that it might be possible that that part is never going to fail by fatigue. Then, these numbers, this shape of the curves is going to tell me that if the part is going to have, like it is represented here, a finite life, or it's going to have an infinite life, meaning that if a part lasts, let's take this case, a little bit different than the other. If a part lasts or fails in some part of this stage, I'm going to say that that's a kind of a part that has infinite life, even though it fails here, but it has an infinite life because you're going to see that sometimes, well, maybe in the other part, that it might be possible that when you do tests at a certain, let's say, stress applied, the part doesn't fail, and then you just stop the test. And then if the test goes beyond certain limit, you say, well, this part has infinite life. But if the part kind of fails in somewhere in this range, then you say that that part has a finite life, and then you're going to say, hey, you know what? This part is going to last this many years. So let's put it in that way. Questions? Good. This is another kind of representation of experiments where you take the material and plot the fatigue limit you have found for that material and versus that ultimate strength of the material, and you're going to get something like this. Yeah? And approximation have said that if you want to know what's the theoretical endurance limit of the material, then you have to know what's the ultimate strength of that material, and divide it by two or kind of take half of it, and that's going to be the theoretical fatigue limit of that material. Now, you're going to find that in different cases that experimentally, if you make a bunch of experiments with several different types of material, and then you throw a line trying to intercept as many points as possible from those experiments, you're going to find that the coefficient to fit that line is going to be 0.38. And meaning that you could say that, well, experimentally, if you want to know what's the endurance of that material, then take the ultimate strength of the material, multiply by 0.38, and it's going to be, so it's even way less than the theory says, but we work with the theoretical values here. And also theoretically, it said that that limit, endurance limit, is not going to be over 700 megapascals. So that's the top limit that you're going to find. So that's according to theory. But imagine how it is. So to answer the question, okay, what's the endurance of the material? Well, tell me what's the ultimate strength of that, and then I will multiply by 0.5 or divide it by 2, and then I will tell you what's the theoretical endurance of the material. Let's call it theoretical because that's kind of, even it is coming from experiments, then it's going to consider like the base, the raw number for the endurance, and a raw number that by itself is not usable per se, and we're going to see what's affecting that number there. Good. So now we know how to calculate this raw number, the theoretical endurance, or coming from experiments. Let's put it in that way. Endurance limit, yeah, endurance strength. To call it kind of similarly to what we have been calling with yield strength, and then you have the stresses applied compared to the yield strength. Now we're talking about fatigue strength, and then we're going to compare it against the fatigue stress. Let's put it in that way. And now this is the raw value. It's not the one we're going to use, but it's the raw value, and that's important to know. The next thing to see is that, yeah, well, we have been talking that fatigue appears where variable load is present. But variable load, I mentioned also, that has different definitions or different characteristics. And this is where these charts come very handy. The first two charts here are the kind of idealized versions of what a variable load is. You're not going to find in practical applications something close to those two top charts. They're very well neat, they are very organized, clean. You're not going to find that. You're going to find something very close to this button chart. So if you measure variable loading on equipment, it's highly possible that you are going to find it like this bottom chart. When you measure that, let's say either stresses or load, let's put it load because loading you can transform it into stresses later, but let's call it about loads. Then, if you measure the load with respect to time, and then if you have a very high sampling frequency, meaning that you're measuring the application of load every, I don't know, 1,000 times per second, 1,000 hertz, an exaggeration, but it's valid here, then you're going to find that this has this kind of very noisy shape. And then you have to do certain post treatment. In here, I can see, maybe you can see, but for example, the blue line represents the fx, and then the red line represents the fy. So I could assume that that picture, actually I took it about 3 years ago, comes from certain testing that has two types or load applied on two dimensions. So that's why it's appearing there. Now, this one in the middle you can find also, definitely. You can find that. And the important thing to consider or to take home in this slide is that you can start here. This can be the results of your experiment, and then you can smooth out all of these uh, peaks and noise and everything, get rid of many stuff that doesn't convey any information, and you can transform it into this, which is way more, let's say, uh, you can process it more convenient way. And also you could try to have certain idealization of this part and transforming into this one. Why not? So it depends on the degree of complexity you want to work with. Important things to take away from all these charts is that you're going to have a maximum stress or load. Let's remember that even though here is written load, load can be transformed into stress by applying certain considerations as we have seen before. And then you're going to have a maximum stress or maximum load. You're going to have a minimum stress or minimum load. And then you're going to have an average of those. Three concepts plus the concept of amplitude, which is kind of what you find from top to bottom, from the maximum stress to the minimum stress. In this idealized version, something like that. In this semi-idealized version or smooth version, you can find this one and this one, and then and so on. If I try to replicate it in the, let's call it original case, coming from instruments or measurements, I could say, well, you know what? I think, from this chart, this is going to be my maximum stress or load, just considering the blue line, and then I'm going to consider that the minimum is going to be somewhere. Maybe here it's going to be the sigma minimum. Yeah, it is possible, but it's too noisy. Then the way this let's say load variation is positioned vertically with respect to the zero axis, meaning this one, is going to give a specific name to the type of loading. Let's see it. Let's focus first on these ones. So if the variation, if the variating load doesn't touch the zero line of this Cartesian system measuring stress versus time, then I'm going to call it fluctuating stresses or fluctuating load. So it's the same load. The only thing is that the minimum of kind of the curves doesn't touch the zero line here. If kind of it is, let's say, nicely distributed, around the zero axis, meaning that sigma, the amplitude, you can divide it by 2, and then you can find that the minimum and the maximum, when you take the average of both values, it gives you exactly 0, like it's represented here. Then we are going to call that case as completely reversed loading. Thirdly, if you have a loading case where the minimum of the curve touches, kind of is coincident with the zero line, then we're going to call that loading case as repeated stress. Then by knowing how this is positioned, this variation is positioned vertically in this Cartesian axis, then I can give it a name. And then if we use these names, we're going to know what we're talking about. A side note here is that as this curve can be away from the zero axis in the positive side, it is possible that this curve can be also presented in the negative side without touching the curve. And also a fluctuating stress, but it's a negative one. Sorry for the mess here. But this one is located in the positive side, but physically you can have it also in the negative side of this uh, Cartesian axis. Then we have, according to the way the curves are positioned vertically in the Cartesian axis, we're going to have fluctuating stresses, completely reversed stresses, and repeated stresses. And then we are going to know that depending on what we're calling, so we're going to have certain characteristics. Why is that? Well, we need to use certain features extracted from that curve, features extracted from specific points of the variating load. For example, the first one that we're going to talk about, stress ratio, is simply the ratio between the minimum and maximum stresses, as simple as that. Then we are going to have the average, which is just a statistical average of between the maximum and minimum. Alternating stress, which is going to be kind of it's going to measure the semi part here of the curves, and is just finding out what's this small piece of value. But remember that this is the idealized version, and in the idealized version the alternating stress uh, number, let's call it like that, is going to be the same. Now if I wanted to do the similar calculation but in here, and I kind of say, okay, but you know what, the average of this is going to be something more or less like this. So what is the alternating stress? Well, it may be possible that I have to make some assumptions about what was the value of that sigma A in that case, but it's a little bit more complicated, but you can get to a certain decision about saying, hey, yeah, no, the alternating stress is going to be this one. But in this idealized case, it's pretty simple because it's just a simple mathematical manipulation of the maximum and minimum stresses. And then above all, we're going to consider that alternating stresses are always going to be positive because of these absolute value bars used here, always positive. And finally, we're going to have the amplitude of that wave that we have over there, and that's going to be defined by the ratio between the alternating stress and the average of the stress. What questions do you have? Nothing? Great. As I mentioned here, it says, let's talk about failure theories, but are now applied to fatigue cases. I believe that's the second thing we need to tackle. And before doing that, we are going to talk about factors that modify the endurance limit of the part or material or design. I hope you can see now the slide because I changed PowerPoints and the slide that says effect of design and manufacturing conditions in the endurance limit. So if that's so, let's continue. What I have here is the, let's call it theoretical endurance limit of the part. And that theoretical value is taken from the ultimate strength of the material, as we saw in the previous slide. Half of it, or 0.5 times the ultimate strength, is going to give you that value there. Now, let's make certain, let's say, let's keep track of something. So I just want you to see this from the point of view of the practicality of mechanical design. So we started with the ultimate strength. So ultimate strength is something that we have accepted as a standard, meaning that that's coming from experiments, from uh, statistical approximations, and it depends on many factors. But we have accepted that, yeah, you know what, we can work with the ultimate strength of this concrete number or uh, very discrete number. Fine. Now, what we are doing here is that, yeah, but we want to apply fatigue, and fatigue, you have to multiply 0.5 times that ultimate strength, and that is going to give you this SE. So if ultimate strength is the value that's going to tell me if a machine is going to, or a specific part is going to fail or not, it's going to break more specifically. Now I'm saying that, you know what, take that number and divide it by 2. So now we are saying, well, it's not going to It's not going to break at that. So let me try to draw something here. I want to have a curve representing the, let me see here, the test. I believe this one. Let me put it a little bit higher. Weight, like this one. Yeah. And then I want to have another one from here to here. Let me just try to, I want to, uh, just a second. I want to draw that curve just to put you the idea of how things are going. So this, we have this curve here. And if I have a tensile strength where I find out all these elements related to yield and everything like that, so you're going to have the kind of the, what's the, well, is the proportionality part or something like that, that, it's just, it complies with Hooke's law and everything. And then you have one small bump here, and then this grows like this until it comes here and it breaks. Yeah. So we know that in this point here, you're going to have what is the yield strength of the material, meaning that after that, the material is going to deform plastically. Let me just change this to this. And then you have this one here, which is going to be the ultimate strength. And we say that if the stresses applied are larger than this one, this is going to break. Now, what are we doing? So we are saying that, if you want to consider fatigue, divide the ultimate strength by half. So if I try to do that proportionally in this chart, in this kind of graph, it's going to be something like this. Let me put the ruler better. So this one here is going to be half of that ultimate strength, more or less. Imagine this. So imagine how much power we are taking from the material by reducing the ultimate strength considerations by half. So no wonder why in some cases, and let me change to that scene right now, why in some cases parts are kind of failing like this. So I don't say that this is half of the, half of the material, so it's half of the design, so it's half of the ultimate strength. No, by chance this picture is like that, and you can see this is very different. It's kind of, this is maybe 1/4 of the whole diameter. But what I want to say in here is that imagine how much are we taking kind of power from the material to resist things in our design, and apply, and besides of that, we are applying safety factors to reduce even more kind of the allowable values that we're using. So, okay, let's keep track of this. So this is the endurance that you have calculated using this theoretical consideration. Now it says, yeah, but this is not the one you're going to use. You need to use this one here. And to get from this one, the theoretical one, to the practical one, let's call it in that way because that's the one that you're going to use in practice for your design, you have to multiply by a series of factors. And if we are seeing ahead of ourselves and knowing how engineering works, most probably each one of those factors are going to be less than 1. And if a factor in this multiplication is less than 1, and obviously larger than 0, it means that I'm going to bring the theoretical endurance value even down, more lower in my design. So imagine the amount of, practically speaking, the amount of, what would be the right word for that? Over consideration or over design we're doing in when considering fatigue is huge. So parts that logically would have to be a diameter D, we're saying no, to compete against fatigue is not D, it's going to be 3, 4, 5 times D. So imagine how larger the designs we are, sorry, devising are going to be just by using this clear shown of fear that we are not taking into consideration many factors here because we don't know them. And then say, okay, let's take a look at those factors. So typically 5 or 6 factors you're going to find in textbooks, and then you're going to have surface finish factor. We're going to kind of go over them. And beyond the mathematics or formula that are presented here, I just want to kind of invite you to take a look from the practical side. So surface finish factor. So the question would be, so would it mean that fatigue is affected for how polished or rough is the surface of the material? Well, yeah, it seems so. So meaning that what would be the best practice then to have in my designs? Is it a very nicely polished, mirror polished part or what? Size factor, meaning that the size affects fatigue? Well, yes. Loading factor, we're going to see that also. So loading affects, obviously, if we're talking about variable load, then loading has to be one of the factors affecting the durance limit of the material. The temperature, as we mentioned, and we can consider temperature as part of the atmosphere or environment where the part is going to be working on. Then reliability factor, we're going to see later, but reliability factor means what's the degree of reliability for those 30 years you said it's going to last. For example, say, no, this is going to be last 30 years. Yeah, but that's an incomplete answer. The complete answer would be it's going to last 30 years, plus minus this much, with a reliability of this. And reliability is that something is going to happen according to what you say is going to happen, basically. And the sixth one is the most critical of everything and the less studied in our academics. It's called miscellaneous effects, meaning that whatever else affects fatigue, we're going to put it in one big basket and we're going to call it miscellaneous effects. Imagine that, miscellaneous effects. So whatever comes, we put it there. So we don't consider them independently, but they're called miscellaneous effects. And they're very complex to determine. And in the end, as we're going to see in one of our slides, we're going to say, you know what, just forget about it and let's use one for that. So let's not take that factor into consideration right now. Let's leave it for the pros or when real cases come. But so far, so we're not going to consider. So we're going to focus on the first five and plus another parameter we need to add there. But it's very not funny, but somehow interesting that the one that is more complex to determine is left out most of the times because we don't know what to put there. What questions do you have? None. Okay. So keep track of this chart. So now we have taken half of the power, let's put it in the way of the material, because we just reduce it by half, and we are working with this point here. Let's see. Surface finish factors. Well, yes, there is a difference in the polishing of the material, and I'm going to explain you why. So if you look at this chart here, and as I mentioned in these formulas here, that these factors most probably go from 0 to 1, as we as engineers suspect, the surface finish factor goes from 0 to 1, as I mentioned, and being 1, mirror polished. And mirror polished on a metallic piece means that the surface roughness is so, so small, so microscopic that you practically can see your reflection on that. And that's called mirror polished. And of course, then you go down, you say, well, it's polished, machined, then, with some notches, with some other stuff. But as an engineer, you can say, you know what, all my designs are going to be mirror polished. And yeah, you can go with that. However, we as engineers need not only to consider the design itself, but the costs associated with the designs, and after that, the type of maintenance or maintainability your equipment is going to have during operation. Because uh, please try to remember my words when you're starting your professional careers that we can do marvelous things on paper that are very impractical for the people who are going to operate the machine because it's nonsense the way we design it. And yes, we can design it, we can manufacture it, but when it comes to do, let's say, the real job, and people have to do some maintenance on the machine, it's a nightmare. It's a nightmare. And then we as engineers, we not need to focus only on the present and the future close future of the equipment. We need to consider the equipment in the whole life cycle that it's going to have, meaning that any design decision we do today is going to affect the person doing maintenance 20 years from now, and then it's going to affect also the disposition of the machine 30 or 40 years from now. So we need to take care of all those steps. And you say, well, all my designs are going to be mirror polished, and then you have to ask yourself, is it necessary to have mirrors polished? Because this is very expensive. This costs money. to do. And maybe your part is not possible to be mirror polished because it's no way to, well, it's inconvenient to do it. And if this is costly, then well, polish machine or what's the part. So it's a decision you have to take. But the interesting thing is that when you go to the ideal case, mirror polish to other cases, your uh, endurance gets punished by these factors. So let's imagine machine part, it's just, it came out of the lathe or the machine tool you're using. This is the ultimate strength of the material, then, meaning that you have to multiply your endurance by zero point 0.8. So imagine that you were here already. And then now it said, well, you know what? Because of the surface finish factor, you have to multiply your endurance by zero point 0.8. So you're bringing down zero point 0.8. So that's equivalent to say that if I divide this into 3, 4, 1, 2, something, it's something like this. So you're bringing it down to here. So you keep punishing that. You don't need to know exactly or have these curves, but there is a good approximation for the surface finish factor that depends on certain coefficients, which are dependent on the type of finish and kind of the ultimate strength of the material. Now, this is very important. Why surface finish factor is important for design, for fatigue? Well, when you have a mirror polished surface, you're practically washing away or polishing away, that would be the word, most of the imperfection of the surface, meaning that there are not these small uh, well, points of imperfection where micro cracks can start, or their their negative process. But if you have a very, let's say, rough finishing your material, then you might have a bunch of imperfections, and those imperfections are going to be the entrance door for fatigue start, for a crack. That's why surface finish is important in fatigue design. Question so far? Size factor. And size factor is also important because it depends on something very silly but true. So the larger the the element, the structure, the machine, your kind of the machine element you're designing, the most probability you're going to have imperfections on that. So the smaller one, the less probability you're going to have imperfections. So it's silly, but size factor, is something depending on that. And look at this, size factor is something like KB and is kind of up to 254 diameter, sorry, diameter D, if we're talking about round bars, where let's say you can use this D value. However, what about if you're using a square part or a profile or a complex shape? But it would be interesting to know this that, so let's put it this way, these values here, if I try to make a kind of a simple calculation, let me try to do it right now. So if I take, for example, a diameter of 50 millimeters, which means that this falls in this category here. And I apply that formula over there, and I say, well, you know what? The size factor or modifying factor due to size for the endurance is going to be, in this case, KB equal to 50 millimeters divided by 7.62. And then that's going to be to the power of minus 0.17. Let me see how much this kind of results. I'm just going to make it because now it interested me. So 50 divided by 7.62, and that I'm going to raise that to the power of 0.107 negative. How imagine that? 0.82 if I round it up to the second decimal. 0.82. Then imagine that I'm using a round bar of 50 millimeters with certain, say, normal polishing here, about 0.8. sorry, yeah, and then I need to reduce that by 80% again because of the size factor. So I keep penalizing the value of endurance I found. And that's going to continue if you get the idea, no, going down and down and down. Imagine that. Now, as I mentioned, so well, this is very clear, diameter D for a round bar, but if you have a complex shape, of course, people, engineers, designers knew that, and then they came up with a with an effective dimension called DE, which translate the equivalent of a round bar to a complex shape piece, like rectangular, or this, for example, H beam or I beam. You have there this U channel you have there. So this is a way that you're going to find in the literature or design standards that when designing for fatigue and it's a complex shape, please use this effective dimension to account for size factor in fatigue. And it depends on kind of the equivalence comparison is made according to the area used to withstand the forces of the load. Loading factor. Loading factor is another factor that is used because when we calculate the endurance factors in stresses, in tests, uh, the predilect or gold standard used for that test rig or device you're using for testing fatigue failure in certain mechanisms is going to be reverse bending. But your application might not be a case of reverse bending. Reverse bending was the case that we saw the aluminum part, the first video I played for you, where it broke due to a crack in the middle. So that's reverse bending, and that's the gold standard. Let's put it in that way. But you can have no reverse torsion, or you can have, let's say, other type of bending, like it says the reverse axial load. So as it is not the same case as presented in the test rig, then you have to do certain equivalence between one load variation type and then to the other one. And it says here that, well, if your case is going to be reverse bending, then okay, leave it like that. So it's going to be one. You don't have to modify anything because that corresponds to the gold standard. However, it's going to be a reverse torsional or shear load or something like that, then you have to, the case of the reversed torsional or reverse shear load, well, depending if it's a ductile or brittle material, then you're going to have 0.59 or 0.8. So, but imagine this. Imagine that you have a case of reversed torsional, a ductile material subjected to reverse torsional loading. So now you have to cut almost by half whatever is left from the value here. So you just bringing that down and then over dimensioning your material. Basically, that's what you're doing. You're over designing this, over killing it. Temperature factor. Temperature presents an interesting response in fatigue. So you can calculate it something like this. You can use this formula. No issues. You can go away and say, well, what's the temperature we are going to be working with in our design and input it here, and that's going to give you the modifying factor according to temperature. Temperature access is interesting because actually in a range, endurance gets favored instead of being punished as in the rest of the modifying factors. And that kind of, yeah, it's here. I wrote it here. So it says here, experiments with temperature-based data shows that fatigue endurance increases slightly with temperature until it hits a range of 200 to 60, 100 Cs, where it starts falling. So meaning that if your design is before, for example, is less than 200 Cs, then you're going to be favored due to temperature. But after that, temperature is going to hit you, and then fatigue and the endurance is going to be penalized, tremendously, and it's going to go down. And it makes sense because when with temperature, for example, yield uh, is kind of more probable. So yield strength is modified and ultimate strength is modified. Definitely, there is a great impact on the material depending on which temperature you are using in your kind of in the environment you are going to have your part working on. But no, but it's interesting that temperature might favor your design in certain cases or in certain regions. It's something that's an engineer, even if you don't remember the formula anymore, when you start working or trying to start designing things. But one main idea you have to take is, oh, yeah, but temperature at some points favors endurance, which reduces the chances of fatigue failure. So let's put it in the way, very simplistic, but it's happening. Reliability. So as I mentioned, reliability, it comes from experiments, from statistics, and we have to account for a level of certainty, and the level of certainty is included in the calculation by using a reliability modifying factor. And as you see here, let's look at the stream. Oh yeah, not the stream. If you want to have a, how to put it, if you want to say with a 50% of certainty that the time you say it's going to fail is going to be accomplished, meaning that if you say no, this is going to fail in 30 years, if you want to have a 50% assurance that that's going to happen, well, yeah, leave it like that. But if you want to have a 90% assurance that that's going to happen, it's not one. You have to multiply it by 0.89. And if you want to have a close to 100%, well, reduce by a bunch. So we are being left with nothing to work with. So that's why design against fatigue results in larger pieces, larger designs, or engineers trying to avoid high loads, high load variation, or large amount of cycles. But when that's impossible, then you're going to end up with oversized machine elements, oversized designs. So that's why. And miscellaneous effects is like, something that is very complex to determine, as I mentioned. And I listed a few of them. For example, when you machine a part, or you use forged, you're forging to create a specific part, or laminate things to create round bars or plates. So you are inducing stresses. Manufacturing processes include certain stress relieving practices, but you cannot be sure that all internal stresses due to the high amount of energy applied to the part to be manufactured at the beginning is not going to go out. So you're going to, and there are going to be remains of spots of high stresses inside of the part that you don't know where, you don't know if there are, how many of them there are, or what's the region of the whole part that is, contained with residual stresses. So, for example, if you've seen a little bit of welding design or welding calculation, welding is done by heating up a couple of parts, adding a third material to join them, and that's a lot of energy you're putting there. And then when everything is heated up, it melts, and then the three parts are melted and joined. But then when it cools down, there are a bunch of stresses that they were not there because you put a lot of energy, and then that energy, not all of that went away. Then you have to do some stress relieving practices to normalize and ease out the whole uh, higher stress situation in welding so it doesn't break suddenly in that area. The same happens here for a typical material when you go to buy a round bar, for example, and that bar has been laminated from a cold, I don't know, other part, and then the whole process of manufacturing by modifying shapes using high amounts of energy induces stresses inside. And then, yeah, you can try they can try to relieve it by heating it up in ovens to a certain temperature for a certain time and see that it cools down and smoothly. But you don't have guarantee of that, and that's considering the miscellaneous effects factor. Then corrosion affects fatigue limit of your part because corrosion creates some pits or pitting on the surface of the material, and pittings are kind of equivalent to the surface finish factor that they are the door for crack initiation. Coatings, if you have coatings, well, that could improve or could, deteriorate the capacity of bearing load in terms of fatigue design. And then you have the type of cyclic frequency, fretting. Fretting is small movements between each other, and then that's not so considered. So there is an universe of miscellaneous effects that you could consider in your design. There are so many that people, sometimes they just, it's difficult to consider. For our case, we're going to take one. What questions do you have? Great. There is another mm, element we need to consider in fatigue design, and that is stress concentration. Stress concentration is included in fatigue design using a parameter called notch sensitivity. We're going to see how to calculate it, but there are books dedicated to stress concentration factors. One of the most famous books for this is the Peterson Stress Concentration Factors book. It's a book about 500 pages, 600 pages, something like that, where there are tables, charts, formulas that, depending on the design, the shape you're adopting, procedures you're using, it's going to guide you in terms of how stresses are increased or how stresses can be kept in line with what you want, depending on, many of those factors. It's a very nice book. I recommend if you can have it and then you're going to proceed in the life of structural design or machine element designs. Peterson Stress Factors book is something to have in your library. Now, stress concentration factor is defined as the relation between the maximum stress you're going to find and the nominal stress. But again, this is not something that you consider in the whole piece. Let's remember that when we talk about stresses, we started our subject by studying one specific point of a part. And we said that that point was going to have a state of stress represented by a stress cube, something like that. And when we talk about stress concentration factor, we have to assume it's the same. So stress concentration factor is not something that you are going to see in all the part, but you're going to see in certain areas of the part, like in this one. And this is a very simple and nice figure because if you consider that these lines are supposed to be the lines of stress values flowing from one end to another, the same amount of stress, let me put it very simplistic, same amount of stress existing in this area is conserved and presented in this area, meaning that at some point it had to be compressed, and those points are these ones. Very simplistic kind of explanation. No, it doesn't depicts or describe the full complexity of the topic, but let's take it anyway. It's like to put, water, the same amount of water to in a diameter reduction. For sure, something needs to happen there, and then that happens is an increased stress at certain points, and that gives birth to the stress concentration factor, which is the relation between the maximum stress and the minimum stress, but of a point, not the whole thing, of a point. Good. Then what we do with that maximum nominal stress, well, for sure I know the nominal stress because when let's take an example, a beam, and I can, have a beam, loaded beam, I can do the uh, shear force and bending moment diagrams, and then I can calculate the nominal stress at certain sections, and then if I go further, I can pick a point of those beams, and I can calculate the state of stress of that point and calculate kind of the nominal stresses. But then, if I know the point, I can also know the maximum stress. How can I know that? Well, depending on the type of imperfection you are dealing with, then you are going to have a certain level of stress concentration. And this is an example. This is kind of a plate, and a plate is subjected to axial tension, this one and this one. Imagine that this is a force here applied, and this is a force here, the same force. And for sure, the stresses are going to be represented like this, but in the middle, there is a kind of hole, an ellipse oriented in this way. Definitely in the vicinity of this ellipse, stresses are going to increase to a certain level. Increases are going to disappear because there's nothing here, and then it appears again, and then goes to the normal level. However, depending on the shape and orientation of that ellipse, you're going to have larger or smaller kind of increases in stresses. And if you have a completely round hole here, then it's also going to be at a certain level. How much is that increased stress? Meaning these ones here. So this one, and this one. Well, the maximum stress is going to be this one. Imagine having a an elliptical hole oriented kind of with the largest axis perpendicular to the direction of application of the force increases locally the stress by 5, by 5. So if we're talking about sudden rupture in a machine element, then I know that if I need to, by considerations or by design or kind of demands of the design itself, there has to be an elliptical hole, and that elliptical hole has to be kind of the largest axis has to be perpendicular to the application of the force. I know that in the vicinity of that ellipse, I'm going to have an increased stress of 5 times the normal stress applied there. So imagine that. So that's equivalent to say that I would have to use a safety factor larger than 5 to overcome that problem where is happening right now. When the largest axis of the ellipse is aligned with the application direction of the force, then it's going to be the maximum stress found here is going to be 2 times the stresses or normal stresses applied there. And if it's a circular hole, then it's going to be 3 times. Imagine that. Who would have known that a simple ellipse on a in a plate would create so much problems in the design? And again, that you would have to overestimate certain sizes, overestimate certain safety factors, so you can take in account those increased stresses, which are called due to the concentration of stresses on localized areas. So imagine that is a lot to consider. So design is a beautiful process that gets uglier when you start going into the nitty-gritty details of it. This is more or less the same example of that. And I want to make a distinction here, well, not right now, but later with the nomenclature used, so it doesn't confuse us. But for example, look at this example here. This is a round bar subjected to bending, and it has a hole in the middle. So imagine how much that increases the stresses on that. So depending on the relation between the diameter of the bar and the diameter of the hole, then you can have a factor concentration, let's say index or number. It could be even up to close to 3 times the normal stresses presented on the bar due to the moment applied on that. And the most important thing is that if you have at least one hole in the bar, so its stresses are going to be higher in the vicinity of that hole there. So you have to take that into consideration all the time. So whatever breaks the smooth flow of stresses of your part, translated that means whatever different shape from the original you are going to have on your design, then you know that you're going to have stress concentration in certain parts, and then you have to take care of that. For example, imagine that you're designing a shaft like the one we were seeing the other day, something like this. So you have a part to position the bearings, and then you have a larger part where you're going to position, for example, maybe a gear. Then you have a shoulder here, and then that's going to be reduced to this part here, something like that. So these points here break the fluid of normal the stresses created inside, and then this is going to induce increased stresses that you need to account for that. There are measures to reduce the effect of those stresses, countermeasures, if you can call it that way. You can use them, to not to make it so deleterious in the end. Let's look at another example. Change in diameter, for example, look at this. So if you have a difference in diameter of a shaft, and this is a single shaft subjected to a tension load, and even in this case, you can find, well, according to this table, according to these values, that you can have stress concentrations of 2.14 times the normal stresses applied there. Imagine that. And if the bar, you have the same case, but subjected to bending moment, then it could be up to 3 times. The increased stress in certain points. And basically that's going to happen in this area, in here and in here. What questions do you have? Let's look at another case. So torsion. This is for the case of torsion. We're talking about that you can have, well, according to the table, because you can have a wide range uh, R versus D, relation or ratio. So it's not just confined to this table, but this is a representative table of certain values. And in this case, if a bar with a change of diameter step, let's call it that way, subjected to torsion, then you're going to have up to 2.2 increase stress in those points there. And then even this small groove that you have here, look at this. This small groove that you're going to see in many machine elements, this is very typical of machine elements, can increase your stresses in a certain points up to 2.85. Imagine that. Imagine that. Let's see. Again, groove with bending moment, groove with torsion, the previous one groove with axial with tension force. And in these cases, you're going to have even, 3.6 for this table or 2.5. So, so when, now seeing back when we were talking about this beam, we were designing in the exercise sessions last time, and the profile I chose in that example resulted on a safety factor of 1.2 when you compare the section modulus of the selected beam against the beam that you should be using there. I was well, 1.2 is a nice safety factor, but now if you're going to have stress concentration factors that is going to ramp up your localized stresses by 4, then a 1.2 safety factor doesn't make sense to be using there. Of course, these are different cases. In the other case, in the case of beams, there are static elements. They are very, let's say, conservative and very robust. In this case, we're talking about parts that are going to be subjected to variable loading, and then discontinuities that are going to forcefully induce stresses in them or increase stresses. And that comes to find what I mentioned. So stress concentration is used also in fatigue design via a parameter called notch sensitivity. And the parameter finding out the notch sensitivity, which is a sort of formula that we could, let's say, use also or calculate according to certain charts, is going to give me a factor of Kf. Now, this is a very big distinction I want to point out right now. So K, big Kf, not to be confused with, let me go back to this Kf you have here. Miscellaneous factor would be a small kf. I don't know. I should change this in the future, but this is a small kf representing the miscellaneous effect to reduce the endurance limit. But the one that I'm presenting to you right now is big KF, and this big KF is something that we're going to use when calculating fatigue in a few slides. So not to be confused. How can I write like this? Kind of if I write something like this, KF, not to be confused with this big KF or something like that. So, and this is miscellaneous effects, and this is kind of modified concentration factor, not to be confused. And notch sensitivity, then, it's also calculated with tables and it's very well documented. No. All right. Questions so far? Yep. Similarly to the static case, where we use for ductile materials, the Tresca theory or maximum shear stress theory, we use von Mises theory. We could have the possibility of using the principles, maximum principal stress theory that is also used in brittle materials or the Morse theory also for brittle materials. When we talk about fatigue, we could use a different approach or different theories, let's put it in ways. These three mentioned here are one of the most used. The Soderbergh methods, Gerber methods, and then Goodman method and modified methods are also used there. Now, I need to make emphasis that fatigue design and let's put it crack analysis or failure design due to, let's say, cracks or this kind of other phenomena are very complex, and there are a universe of, let's say, methods to be used or to pick from when designing for these phenomena. It's important to emphasize something that I have in mind is that I mentioned that later, but it's worth mentioning right now, is that damage in equipment is cumulative, meaning uh, as long as you're using a machine element on a equipment, any damage that is going to be kind of induced in the machine, it's not that when you stop the machine, that damage is going to be, let's say, healed. No, no, the damage is cumulative, and that's going to give birth to another type of theories, such as the miner's rule for cumulative damages and stuff, where instead of considering that damages are only when it's working. No, no, damages are always accumulating in your part, and that's something that is very complex. And there is a lot of study on those topics that are not mentioned in this course, but I just want to make you aware because definitely if you continue the master studies in the university and you take this course called fatigue design or fatigue something, I believe it's called still, you're going to see a lot of material there referred to cumulative damage and kind of and these three methods that I'm showing right now, like Soderbergh, Gerber, and Goodman. So it's a lot of there are a lot of information about fatigue, and I believe that the reason we have that wealth of knowledge base is because fatigue is so common in mechanical structures, at least not only, but there are pretty common metallic structures and you know, elements manufactured out of steel that a wealth of experimentation has been done on that. Good. Then let's take a look at something to start materializing those three theories. So one thing that I wanted to show you first, even though it is not coincident with the list I presented before, the order, is this Goodman diagram. And this Goodman diagram here presents three big areas, so green, orange, and red. Green mean that, okay, first let's describe what are these axes. So in each of the axes are stresses. So this is stress and this is stress also. And each one of those I'm plotting the yield strength of the material and the ultimate strength. Logically, yield strength is lower than the ultimate strength of the material. Now, if I have a case, a machine element subjected to a variable load. And let's imagine that that variable load is something like in here. So you are representing here the maximum stress, this is the minimum stress, and then this is the average. So this is to be something like sigma m, and this is sigma m here. Those parameters extracted from the cyclic load charts we saw before. If that is located in this region, kind of constrained by the ultimate strength of the material, this point. If it's located in this green area, it means that it is a safe life and you shouldn't be worried about fatigue. Just don't calculate fatigue. Just leave it like that. If the loading case falls out of or away from the yield strength of the material, ultimate strength, the worst, something like that, then you shouldn't be worried about fatigue either because it's not going to fail because of fatigue. It's going to fail because either yielding or rupture. So you need to take care of that. But now, if you find yourself in the orange section here, then you need to take care for fatigue. And if you need to take care for fatigue, you need to answer the question of how long it's going to last, how many cycles. Remember, that with fatigue, you also answer the question, this is going to last 3 years, 10 years, 20 years, 30 years, something like that. So if your loading case falls in the orange area, then now you need to consider fatigue in your design and answer the question on how long it's going to last. The figure we're seeing on the right, bottom right, is the same figure, but now considering the number of cycles to fail. And what it does is that now you have this line, which is the mean stress basically of the specimen is equivalent to this line here. They put it in black maybe. This line here and this line here. So this line here is equivalent to that. And now the areas are not marked by straight lines, but are marked by these curved lines here when you consider these cycles to fail. But this is a very good indication on what to follow, on what to, let's say, proceed. And then let's take a look at the theories because they are they're very simple. Let's say, for example, this case on the Soderberg kind of on the Soderberg line or case. To determine if your how is the case in situation of your application, you are going to draw a Cartesian axis, and you're going to draw in one of the axes, the horizontal one, you're going to draw the average stress of your loading case, and you're going to draw the amplitude of the stress in the vertical axis. Then, in the horizontal axis, you're going to locate the yield strength of the material, and in the vertical axis, you're going to locate the endurance limit of the material. The line formed by these 2 points is going to be called the Soderberg line. Okay? Meaning that inside of this line, or to make it very simple, whatever loading case you have that falls within this line here is going to be okay. And additionally, if we have a point like the one presented here, a case, this is the loading case of your application, the distance existing between this parallel line and this one here is going to be your safety factor. Great. Now, interesting would be to know how to plot that line so we don't have to refer to a Cartesian axis every time we have a loading case and we want to apply Soderberg fatigue failure theory. Let's put it in that way. By the way, in this case presented here, we are not answering the question of how many cycles this is going to last. We don't know yet. We just know that, according to Soderberg, that's going to fail. That's going to fail, after many cycles, but we don't know how many cycles we're talking about here. Well, it is mentioned here. So it's going to fail. The line represents failure points. Actually, let me put it in yellow because it's more representative of the graph. Line represents failure points after a certain number of cycles, but we don't know yet. We don't know yet. Look at this. This would be the Soderberg line. No, the line drawn from the endurance limit to the yield strength of the material, kind of representing this horizontal and vertical axis. And this is going to be your loading case, this one. And the difference between these two is, well, according to this example, is 1.5, and that represents something like, 1.5 safety factor, something like that. Then, if I use the same Cartesian axis where I have the average and the amplitude here, kind of the axis, and then I have here the endurance, and I have here the yield strength of the material, I know that this is going to be the Soderberg line. However, the line drawn from the endurance of the material up to the ultimate strength of the material, that line is going to be called as Goodman line. And if I fit a parabola between those 2 points, that's going to be the Gerber parabola. And those are the three, let's say, fatigue failure theories we could use here. They come from experiments, and there are certain loading cases and materials that would be described better by using Soderberg. Others might be described better by using Gerber parabola. But the idea is that they come from approximations on of experiments, and and they say, well, we could use a straight line here, we could use a parabola here. So, for example, in this in this example here, these small dots presenting in this part here are, they say, failure points. And those failure points, when you fit a line, cross them, the best fit you can get is a parabola, and then that's what's called Gerber parabola in that case. If we take a look at the Soderbergh line can be analytically written something like this. Look at this. You have the amplitude of your variable load, average stress of your variable load, and then you have the material characteristics here in the bottom. You have the endurance limit, and then you have your yield strength, and then you can solve for the safety factor of that. So that's the analytical way to do it at this point. So you don't have to refer back to a chart or anything like that, but you can do it by using a formula. We have the similar part for Goodman in here. But in this case, instead of using the yield strength, we're using the ultimate strength here. And for Gerber, what we are doing is that we are using kind of a square term here, which is represents of a parabola in this case.